All right, now let's start talking about Chapter 2, some basic chemistry, in particular as it applies to living systems. Um, Chapter starts with a story of this thing called the Devil's Garden, and we'll talk about this in more detail in class, but it's an interesting situation, which you could call a symbiotic relationship or a mutualism between an ant, a particular species of ant, and these plants, in which the ant essentially is the caretaker of the plants and takes care of them. And so these, what they call the Devil's Garden, forms there. Um, and so the plants, the ants live on the plants and basically keep other plants away by essentially killing those other plants, as we'll see. Um, so it's an interesting situation where the ant is using chemicals to suppress other plants to um, protect and take care of the ones that it lives on. So you might say, I mean, people, humans, are sometimes, um, well, we do this a lot. We sort of manipulate our environment to our advantage and suppress things we don't want around and nurture things we want around. And so essentially the ants are doing the same thing here. Again, we'll talk about that a little more detail in class. All right, so as you all learned in chemistry, of course, we have many different elements, and those elements have unique properties. And when you put uh, different elements together, you get compounds like sodium chloride. Um, and as we talked about in the previous chapter, of course, these things can have emergent, unique properties that are different from the individual elements. Um, so we're not going to talk about all of the elements because when it comes to life, really it's a subset of the elements that are most important. And in particular, you can see these four, oxygen, carbon, hydrogen, and nitrogen. Those are, you might call the big four. I like to rearrange the order a little bit and think of them this way. John, carbon, hydrogen, oxygen, nitrogen, the big four. You can see in living things, they comprise about 96% of the mass because, of course, living things mostly are made of water, and water has oxygen in it, and oxygen is a relatively heavy element of the four, and so that gives us most of our mass. You can see these others that are found in much smaller proportions. Of course, calcium, we know you drink it in your milk, and it's good for your bones, um, and some of these others as well. So we can think of these, as your book describes them, as the elements of life, the most important ones. Um, okay, so just some review. As we know, elements have subatomic particles. Of course, the protons and neutrons in the nucleus, giving the atom the vast majority of its mass, and then the electrons that are orbiting around um, with their negative charge, essentially contributing almost nothing to the mass of the atom. Um, of course, the protons positively charged, the neutrons neutral. Electrons are found in orbitals, and as those electrons can move between orbitals as they get more energized, they can move into orbitals further from the nucleus, and as they lose energy, they can go back down into lower orbitals. Um, the orbitals um, generally have a certain number of elements. As we know, the first orbital will have a couple of electrons. The second typically will have 8, and the third will have 8. And that's sort of our rule of thumb, particularly in biology classes. As you learn, as you go out, they can get more variable numbers, but we'll stick with that for now. Um, So here's a subset of periodic table again with, of course, there's carbon. Oops, carbon. Where is it? Hydrogen, oxygen, and nitrogen are big four. And so you can see the number there, the atomic number, which is going to be our number of protons that it has. You'll recall that it is indeed the number of protons that essentially defines the element. Carbon atoms will always have 6 protons, no more, no less. Nitrogen 7, oxygen 8, the atomic number. And so typically carbon will have its 6 protons and its 6 neutrons for an atomic mass or mass number of 12. But you'll probably recall that that mass number, when you have more protons and neutrons, is not exactly 12, and carbon is 12.00 something. And I'm sure you'll recall that's because the number of neutrons can vary. The vast majority of carbon atoms have 6 neutrons, but some have 7 and some have 8. You can have carbon 13 and carbon 14. And it is those isotopes, and those are the various isotopes, C12, 13, and 14, and those heavier isotopes are what make our atomic mass slightly more than 12, because we have to take all those isotopes into account. But it is basically 12 for carbon. And 16 for oxygen. Again, not exactly 16, but pretty darn close. And of course, here you can see our orbitals. And this is going to be very important in that, as you learned before, it's so let's look at, of course, we have fluorine and chlorine. No, I'm sorry, let's look over here. Neon and argon. So neon and argon, you can see that outer orbital has 8, 8, and 8. So those outer orbitals are full. But when we look at all these others, so fluorine and chlorine, their outer orbital has 7 electrons. So they'd like to get one more to, as I say, be a happy atom. And so it's when you have these unpaired electrons in an outer orbital that atoms like to get together and form bonds so that they can get all the electrons they would like to have. And perhaps you'll recall we have this term electronegativity, and you can think of that as how desirous an atom is for electrons. And so fluorine and chlorine are very electronegative. They really want to get that one last electron, so they're very reactive. Whereas over here, lithium and sodium, not so much. In fact, they only have 1, and they are more than happy to give that up if the situation arises. So, of course, when we take sodium chloride, chlorine really likes that electron. Sodium is willing to give it up, and as you'll recall, they form an ionic bond. But I get ahead of myself. Okay, so here's some of the structures you've seen in the past, the way we can think of these different molecules, these different compounds. And so which of these is a compound and which is not? Let's see, water, methane, those are compounds, right? Because they have 2 or more different elements, whereas our H2 and O2, while they are indeed molecules, they're technically not compounds because they just consist of a single element. Of course, in our Lewis structures, you can have the dashes that represent a bond, a covalent bond, a pair of electrons shared, or you can have the dots in there to show the actual electrons, the paired ones and then the unpaired ones in the case of water here. And there's our example of our classic example of the ionic bond between sodium and chlorine. Chlorine very electronegative, will take that one lonely electron in the outer orbital of sodium. And sodium, because it only has one in that outer orbital, will tend to give it up. Now keep in mind, hydrogen is a little different. It only has one electron in its outer orbital, but it doesn't give it up because it only has one. Whereas, of course, lithium and sodium have others, so they will give up that one electron in the outer orbital. Okay, so ionic bonds, and of course then we have covalent bonds shown by our dashes in our Lewis structure, where we have this pair of electrons being shared. The electrons are spending time on both the atoms. But with some covalent bonds, as you'll recall, for example, water, we have covalent bonds between the hydrogen and the oxygen. There's a pair of electrons being shared there. But the oxygen is more electronegative than the hydrogen, so those electrons spend more time on the oxygen than on the hydrogens. And so this side of the molecule has a slight negative charge, and on the hydrogen sides of the molecule we have a slight positive side, and so, as you recall, we call this a polar covalent molecule. And when you put polar covalent molecules together, the slightly negative side will bond with the slightly positive side in this hydrogen bond, this relatively weak bond, but important bond, as we'll see. All right, another type of bond that you can find out there, these van der Waals interactions. Van der Waals, named after a Dutchman, I assume, because this looks like a Dutch name. Van der Waals interactions. These weak interactions from the orbiting of the electrons around an atom in molecules and compounds, and how at moments in time more of the electrons can be on one side than the other, and so that can give a slight charge to one side of that molecule. And so perhaps we'll try to watch the video of the gecko in class, and we'll take a look at their toe pads and how they've got all this immense surface area on their toe pads, which allows for these relatively weak forces individually but collectively to be strong enough for that reptile to walk up walls and on ceilings and things like that. Quite fascinating. Compounds, shape is very important. And for example, in this here we see endorphins, these molecules we produce. These are sometimes described as these natural painkillers. Here's morphine, which is derived from poppy plants. And you can see one part of the molecule is the same, and that's the part that's important for binding with neurons and inhibiting the transmission of neural signals and basically decreasing pain. And so we'll revisit that more a little later as well. Last thing, of course, chemical reactions. We know that molecules like to react with each other, and so on one side of our chemical equation we have our reactants, and then we have our products. Of course, they have to be balanced on either side. And as you learned, of course, some reactions are generally spontaneous, at least when they are releasing energy. But as we'll see, it often takes some help to do that. And so we'll talk about things like, of course, enzymes, which help facilitate reactions, and enzymes helping, what am I trying to say? This. Enzymes helping to overcome the activation energy needed to get the reaction to go. But we'll get to that a little later. Okay, that's it for Chapter 2.